Welcome to today's video, and the question today is to design a T flip-flop using a functional table below. A T flip-flop basically contains a control signal T, which determines whether the current state of the next state of the flip-flop will be toggled or not. The functional table tells us that when we have reset equals to 1, we don't care what our clock is or what T is, our next state will be 0. And this is our reset state. And when our reset is 0 and our clock is 0 or 1, we don't care what T is, our next state of our flip-flop will be equals to the current state, which means we don't change it. When our reset is 0 and we have a rising edge and T is 0, then we still keep our current state to be the next state of our flip-flop. However, if our toggle is 1, which is our toggle state, then we will toggle the current input to be our next state, the current state of the flip-flop to be our next state of the flip-flop. So let's start by drawing a conceptual diagram of our T flip-flop. And to start with, we can draw. We can say that we have our D flip-flop, okay, with our clock and our output, and we have our input also. And from our functional table also, we can see that we have so our T is going to choose between toggling our next state and keeping our next between toggling our next state, between toggling our current state to be our next state and keeping that current state, that next state to be keeping that current state to be our next state. So in that case, we can clearly see that we have a max, and with this max we can see that our T is going to be the input, and we can also say that we have the toggle state of our input of our current state, where we can say that we have this state here, and we have directly the input from our current state to be our next state. So this will be like this. So T will be choosing either 0. We said here that when T is 0, we keep our current state. So in fact, we're going to say that this is 1 and this is 0. Okay. So then this is going to be the input to our D flip-flop. So we have our D and then we have Q. And this is our clock. And we will also have our reset. And we have Q as our output. So let's name these signals, because we have two signals here that we can see, and we can say that this is our Q next, and this is our, let me make some space here. And we can say that this is our Q register. So this is how our conceptual diagram should look like, and this is going to be our output. We can say that this is our output Q. Great. So then when we have our toggle signal equals to 1, then it means that we're going to toggle our output. We're going to toggle our input to our max here, which in this case is going to be the current state of our flip-flop. And so now we are going to program this, to write this in VHDL. So now let us write the code for this T flip-flop, and I'm using Visual Studio as usual. And I'm just going to put this side by side because I'm going to use our conceptual diagram or our RTL diagram in order to write this code. And so I've already created the t-flip-flop. I've created the t-flip-flop folder, which is what you should do to keep your work neat. So, and then inside this folder, I created the t-flip-flop.vhd file, which we are going to program. And to start with, we are going to need to import our libraries for VHDL. And to do that, we're going to say use IEEE. Sorry, not use. We have to say, and to do that, we are going to import our libraries, library IEEE, and then we're going to use IEEE. And now we are going to define our entities. And this is going to be our t-flip-flop. And then we're going to define our architecture. Okay, great. So now we're going to define our inputs and outputs in the code. And we have T as our input, clock as an input, reset as an input, and then we have Q as our output. So to keep things neat, you just want to put all this in the same kind of column. And now that we've defined our inputs and outputs, now let's get to inside the behavioral, the architecture. And as usual, we are going to have three parts of our circuit here. You're going to have the t-flip-flop part, you're going to have the output part, and then we're going to have the next state part. So we say we're going to have our t-flip-flop. We're also going to have our next state, and then we're going to have our output. So for our t-flip-flop, we're going to have a process which is going to be activated, which is going to have a sensitivity of clock and reset. Okay, so before we continue, we're going to need to have our signals first of all. And to define our signals, we define them in this part of our VHDL code. And we're going to have signal. So we said we have our Q register, and then we also have our Q next. And these guys are STD logic Okay, so we say that we're going to start with our reset, which is asynchronous, which means that it does not wait for the clock. So we say if our reset is active high, is this what we said for our reset? Let's look at the functional table, which says if reset is high, then we are at 0. So yes, this is what we did. This is what is defined in the functional table. So if reset is 1, so if reset is 1, then we say that our queue next, sorry, our queue register, this is the output of our diff flip-flop here. Our queue register is going to have 0. Okay. Else if now we look at our clock. If we have a rising edge of our clock, then we will say that our queue register, queue register is going to get queue next. Great. So we finished our process. So we finished our diff flip-flop, and so now on to the next stage. We know that we have our max, which says that when we say that our queue next is going to get the toggle state of our current state, which is going to be queue register as shown here, when we have our control signal, which is going to be t is equals to 1. Else we are going to get simply queue register, which is not the toggle part for our next state. Okay, and this should do it for our next state. And for our current state, for our output, we are simply going to say that our output is going to be equals to, is going to get the current state of our diff flip-flop, which is queue register. Great. So now we're going to write our test bench to test our circuit here. And to do that, we're going to create a test bench of our T flip-flop. And we're going to do the same thing to import our library. And we're going to declare our entity It seems I found the problem. So let's write our signals. Our signals you can see here. Initialize your clock as usual. And we're going to have a process. And we are now going to have our unit under tests device, which is going to be underwork dot T flip-flop and RTL. Then we're going to have a port map. Then we're going to have our clock. So before we do that, we are going to need to define a few constants, which is our frequency. It's going to be our clock frequency, and this is going to be it's going to be an integer, and we will initialize this to have our clock at 100 microseconds. That's our period to be microseconds, and we are going to have this as our clock frequency as 100 megahertz. And then we're going to define our clock period as time, and we are going to initialize it at 100 megahertz. Let's say 100 microseconds by simply dividing it by our clock frequency. Okay, we would also like to stop our simulation, and we will have a signal that indicates that our signal has finished. So our simulation has finished, so we can say simulation done, and this signal is we can put it as a boolean, and we can initialize it as false. Okay, so now we on our clock we need to toggle it after clock period divided by 2, which is our clock period, and we only do that when our simulation done is equals to false. Else we set our clock to 0. Perfect. So now let's write our process, and to do that we can look at our RTL diagram here. So we can say that let's start by resetting our circuit here and just set it to 0, and then we can say we can wait for clock period. Let's wait for 2 clock periods. So our reset has to be 1, and then after this we say let's okay, first of all, before we even do a reset, let's have okay, so let's just have let's just have it like this. So now after 2 clock periods, let's have our reset to 0, and let's wait, and let's put our toggle, let's put our t to be equals to 0. So to observe if reset is actually, let's have our toggle here equal to 1, and let's wait for, I don't know, maybe 4 clock cycles, full periods, and see if we'll be able to toggle our output with this. So we do this, we say okay, now we put our reset to 0, and then let's wait, and we also toggle 0, and then let's wait for another clock period, let's say another 4 clock periods, and then after this we can say, all right, let's toggle now to 1, let's have our toggle to 1, and since we have a reset to 0, let's observe if our toggle, if we will be able to toggle now, and let's wait for another 4 clock cycles before we say simulation done equals to true. Perfect. Now the only thing remaining is to simulate this and maybe find these errors on this, because I can clearly see there are some errors, but I cannot pinpoint what the error is exactly. Okay, so we are going to do this in VIVADO. Alright, so we're going to create a new project. Fortunately, my computer has been on for some time, and alright, it's been slow now. So we're going to have our T flip-flop, and let's see which folder is it. This is our T flip-flop folder. We're going to select it, then we're going to click next, then we're going to add our files. You can just add all your files here, for your test bench and your VHDL and then we go next. We don't have any constraints, and here you can really just select any general purpose FPGA. Then we go next, and then we finish. So this is what you want to observe. It's updating, and as you can see, we have some errors, some syntax errors. So this time we locate them, and you can see that we have syntax errors on our T flip-flop. And let's see, to get more information on this syntax errors, you can actually run a simulation, and we're most certainly going to get an error, but we are going to get a more detailed error so that we'll be able to pinpoint where our problem is exactly. So open message view. So syntax error near line 22. So there's a syntax error here. I know where the problem is. So this is end process. This is just not end process, and that's it. This was what was all the fuss about. Great. Now let's see if it's fixed. It's updating, and for sure it's fine, right? So we have our test bench as our top level file here, and then we have our unit and our tests. So if you see this hierarchical kind of design here, then you know that your simulation is fine. All right, so now let's run our simulation, our behavioral simulation, and still have another error. So let's see. And where is the error? It is not giving me any. There should be no error. So now that we've run our simulation, we have our inputs and outputs here, and so let's run it to see how it goes. So let's see our output queue here, and then let's zoom in. And so this is our output queue, and we said where is our reset? Our reset is 0. So currently we have our reset 0, and we said it doesn't matter what our T is in this case, as long as our reset is 0, as long as our reset is 1, then the output Q is going to be 0, which is exactly what is happening. So here we set our reset to 0, and we set our T to 1, our T flip-flop to 0, and we can see that when we do that, we still have our reset to our output to 0, which means that we are not toggling because T is equals to 0. But when we set our toggle to 1, you can see that during this falling edge of the clock, or during 1, is still 0. But when we have the rising edge of the clock, we can observe that we have a 1. We have our input, sorry, we have our next state being toggled to 0, to 1, from 0 to 1. And on the next rising edge, since our output was 1, and the toggle is still 1, we have it toggled to 0. And then we wait again to the next rising edge, where we have our current state as 0, and our toggle is still 1. Then we have our output, our next state will be 1. So as you can observe, the T flip-flop is working exactly the way we designed it to. And we can also say that this T flip-flop is slower. It's like this. When we have our toggle on, it is like slowing this clock by 1 clock cycle. So you can observe that for this for 1 clock cycle of this, we have around 2 clock cycles of the actual clock. So we have 1 and 2 for one of this clock or output. So that's it. Our T flip-flop is working as expected, and see you in the next video.